Today's speaker for the Semiva seminar on Kähler geometry and the Calabi-Yau conjecture is Ziqi Liu, and he will talk about Calabi-Yau manifolds and mirror symmetry. Please, Ziqi.
Thank you, Filippo. Thanks everyone for coming. Today I'm going to talk about Calabi manifold and mirror symmetry. Here's an outline of my talk. And first, I will talk about basics on Calabi manifold, and then I will say some words about string theory and explain why Calabi-Yau threefold is important. Then I will briefly say something about mirror symmetry. And then I will explain the early mathematical attempts to understand mirror symmetry. In the end, I will give a feeling on what is homological mirror symmetry. Okay. As before, every manifold in this talk is supposed to be connected. And first, we recall something from the previous talks. Namely, consider a compact complex manifold of complex dimension M, which admits Kähler matrix. Then the following statements are equivalent. A is the first chain class is trivial, and the B is that X admits a Ricci flat Kähler matrix. C is that the X admits a Kähler matrix with restricted holonomic group contained in SUM. But it is true, B implies I follows from basically the definition of the first chain class. This formula is exactly stated in the talk of David. And the equivalence of B and C is mentioned by Filippo at the end of his talk. I refer the audience to his talk. And A implies B is the Calabi-Yau conjecture. And David spent his talk to discuss this conjecture. Okay. Also, David mentioned in his talk that consider a compact, simply connected, irreducible Ricci-flat Kähler matrix of complex dimension M. Then the global holonomic group is either SUM, or when the dimension is even, the SP M/2. And in the first case, we call it a Calabi-Yau manifold. In the second case, it is called a Kähler manifold. The definition is not standard. I mean, people may use different definition for Calabi-Yau manifold. This definition is sometimes called the strict Calabi-Yau manifold. Okay. Then let us say the easiest property of a Calabi-Yau manifold. It says the matrix of a Calabi-Yau manifold is irreducible. Means that it cannot be written as the product of two remaining matrix. It is because then the global holonomic group, the SUM, cannot split as the product of two groups, non-trivial product, of course. Then we see some properties of a Calabi-Yau manifold. The first one is the canonical bundle of a Calabi-Yau manifold is trivial. How can I see it? Suppose that the complex dimension of a Calabi-Yau manifold is M. Then it admits a constant holonomy M0 form, locally looks like this. And this form is in particular a section of a non-trivial section of the canonical bundle. So the canonical bundle admits a non-trivial constant global section, so it has to be the trivial bundle. But on the other hand, a compact complex manifold with a trivial canonical bundle is not necessarily a Calabi-Yau manifold. We know that the first chain class is trivial, so its holonomic group is contained in the SUM, but it can be something like a torus or finite cover of a Calabi-Yau manifold, or it's a finite cover under a Calabi-Yau manifold. Okay. Then we see we're going to see that the fundamental group of a Calabi-Yau manifold is always finite. Recall that for the universal cover of compact Kähler manifold, the global holonomy of the universal cover equals to the restricted holonomy group of the space under the cover, which is contained in the global holonomy group of the space under the cover. Combine this fact with the following famous theorem, which says that a compact Ricci flat Kähler manifold admits a finite cover, which is isomorphic to such a product. Here, T is a flat torus, and the XJs are compact, simply connected, irreducible Ricci flat Kähler manifold, which means that each Xj is either a Calabi-Yau manifold or a Kähler manifold. Combine these two facts, we can see that the Calabi-Yau manifold actually admits a finite cover, which is also a Calabi-Yau manifold with the same dimension. And in particular, it should be a simply connected Calabi-Yau manifold. So it admits a finite cover, which is simply connected. So its fundamental group is finite. It's possible that a Calabi-Yau manifold is not simply connected, but it's really rare. Also, it cannot happen when the dimension of a Calabi-Yau manifold is even. It can be proved by spin geometry, which I will not explain here. So the only non-simply connected Calabi-Yau manifold are odd ones. Also, we need a dimension larger or equal to 3, because we know that the one-dimensional Calabi-Yau manifold are elliptic curves. Then we say that the Calabi-Yau manifold are almost projective, which means that it can be embedded into a complex projective space as a variety, which means that it can be seen a set of solutions with some homogeneous polynomials. But the proof used something that we did not introduce in the previous lecture, so I just explain the whole idea. Recall that in the talk of Filippo, we see that the tensor constant under connection is totally determined by the holonomy group. On the other hand, we know by the local partial bar lemma that this cohomology space is actually the space of constant P0 forms on the Kähler manifold. So combine these two observations, we know that this space is actually the subspace of this space invariant on the action of the global holonomy group, which is SUM in our case. And as I have said before, the SUM preserve the top one, which is this one, and it's clearly preserves the pure one, but it fixed. But one can also see that it fixed no non-zero element of the other spaces. So this vector space is actually 0 for P non-equal to 0 or M, and the space is precisely the one-dimensional complex vector space when for the P equal to 0 or for the top one. In particular, the H11 is equal to H2. And we know that the H11 contains the Kähler cone. Okay, and so we can compute an integral Kähler class. And first, we pick a rational Kähler class. We can do it because the rational number is dense in the real numbers. So first we can choose a rational Kähler class, and then we multiply it with some integer, so it will become an integer Kähler class. And then we can take a closed positive one form, so that the class of this form equal to this Kähler class, and the one then concludes by the Kähler-Vanish theorem, which we haven't mentioned in the previous talk, but I just leave it here. Okay. Then let us see an algebraic characterization of a Calabi-Yau manifold. You know, in general, it's difficult to compute the holonomic group. And so, to say whether a manifold is Calabi-Yau, this definition is more practical in some cases. Consider a complex manifold of complex dimension M, which admits the Kähler structures. Then it admits Kähler Calabi-Yau metric if and only if the canonical boundary is trivial, and these groups are zero for the middle ones. This is more or less the proposition before. One direction is implied in the previous proposition, and let us see the other direction. And first, since the canonical boundary is trivial, we know that the first chain class vanishes, and we can take a Ricci flat structure. And since this canonical boundary is trivial, we know that the global holonomy is contained in SUM. And on the other hand, we know that this space is zero for the middle ones. So actually, we need to have the holonomy to be SUM by what I have said in the previous proposition by the description of the HP0. In this case, we can give an example. A degree m plus 2 hypersurface inside the projective space of dimension m plus 1 is a Calabi-Yau manifold. In dimension 1, it is degree 3. In P2, it is an elliptic curve. In dimension 2, it's quadratic surface, which is a Kähler surface. And so, how to show it? Actually, it can be proved with the method of algebraic geometry. The key word is the Lifshitz hyperplane theorem. To check this condition, one has to use the Lifshitz hyperplane theorem. Okay, so we have finished the first part of my talk. Then I will go to the second part. At first, to give the motivation, we need to know why. Give the motivation for mirror symmetry. We need to say a little bit about string theory. You know, the dream of Justinian is to combine the East Roman Emperor he had with the Western Roman Emperor to the whole one. And for theoretical physics, they want to combine the quantum theory, which describes little stuff, with the general relative, which describes the big stuff, the big picture, to give a theory of quantum relative. And the string theory is by now their best efforts ever. However, the theory is not well understood among people like me. But this motivates a lot of interesting mathematical researches, such as mirror symmetry. we know that the general relativity says that the space-time we are in is a four-dimensional object, which is a three-dimensional space and one-dimensional time. Actually, it's a Pesto-Riemannian manifold on R4. I mean, the underlying smooth manifold is R4. The metric is definitely positive on the space, and it is non-negative on the time. And the string theory says that the space-time is actually 10-dimensional. So a natural question is that what about the other 6 dimensions? This is answered by a bunch of physics. The other 6 dimensions are described by a Calabi-Yau threefold. That's why Calabi-Yau manifold is interesting for them. One reason, not all the reason. I mean, there are 4 types of superstring series. Like basically, there are type 1, type 2a, type 2b, and heterotic type superstring series. And on one Calabi-Yau threefold, one can construct a different superstring theory, and a superstring theory, a given superstring theory can be constructed from a different Calabi-Yau manifold, Calabi-Yau threefold. So there will be natural questions later, but let's now mention that the type 2a superstring theory is constructed based on symplectic structures. And the type 2b is described in terms of complex structures. And it is the natural question I mentioned before, which says that if we can always find a pair of Calabi-Yau threefold, so that the superstring theory described, the type 2a superstring theory described by one Calabi-Yau threefold is the same, is equivalent to the type 2b superstring theory described on another one. If we can find such a pair of Calabi-Yau threefold, they are called a mirror pair. Actually, it is a simplification of the original mirror symmetry question. They treat a certain duality property concerning heterotic string theory. The heterotic string theory can be seen as like roughly a combination of the others. And the mathematical formula of the mirror symmetry question, for any mirror symmetry question, I mean, it's not very clear. Because actually the things in string theory do not really have mathematical descriptions. Here are some major math attempts. Just after the proposal of mirror symmetry problem, people have a Hodge-Diamond mirror symmetry conjecture, which is quickly to false, actually. Also, people have a closed string mirror symmetry conjecture, which is a slight improvement of the Hodge-Diamond one. Then people have Kontsevich proposed the homological mirror symmetry conjecture, which involve more structures. In the end, we have a SYZ conjecture, which I will not mention today. Okay, let's now see the early attempt to mirror symmetry, which are the Hodge number mirror symmetry and the closed string mirror symmetry. Let us pick a Calabi-Yau threefold. Then we have a Hodge number with the dimension of the space of constant PQ form. And we have a Hodge decomposition, which has mentioned before by Leticia in her first talk. we have a certain duality, so we can write all the huge numbers in such a diamond. Actually, by the duality, we can rewrite the diamond to be like this. Here, you can see that we have a duality this direction and duality this direction. So it's that's why we write into this diamond. And since we are considering Calabi-Yau threefold, we actually can do better. We know that these two are 1, and the middle guys are 0. So the only unknowing which numbers are the one in the center. So the key point of the Hoche number mirror symmetry is that the first order deformation of a complex structure is parameterized by a space with dimension this Hoche number H21, and the first order deformation space of the symbiotic structure is parameterized by a space of dimension H11. So if we really have a mirror pair, the first order deformation, at least they should be the same, and the dimension should be the same. So we say that a mirror pair should satisfy that the space of deformation of similarity structure for the type 2A superstring theory will equal to the other one. And the conjecture is that every Calabi-Yau threefold admits such a mirror pair. But actually it is not correct, but it is almost correct. For example, it's true for any degree 5 hypersurface in P4. It mirror pairs a certain toric Calabi-Yau threefold. And I say that it is not true because there exists rigid Calabi-Yau threefold, which means that we have Calabi-Yau threefold who do not have the deformation of a complex structure. For example, we have consider an elliptic curve. Since it is degree 3 of surface in P2, we have a natural Z order 3 action on this elliptic curve. Consider the product of 3 elliptic curve and the action of this product on each vector. The desynchronization of this quotient is indeed a rigid Calabi-Yau threefold, but the proof is non-trivial. One reason that the conjecture is false because we consider two lengths. We only consider the first order deformation space, and a solution is that we consider the global structure. We consider the model space of all complex structure on one Calabi-Yau threefold, and the model space of symmetric form or the Kähler form on the other one. So I claim that we have such a model space, which means that for every Calabi-Yau threefold, we have a model space of a certain complex structure and a model space of complex model space of certain Kähler forms. And the conjecture is that we have a local isomorphism between these model spaces from one side to another and vice versa. The element in the model space of the complex model space of Kähler form is a complexification of Kähler form, which means that there are classes of this form, which omega is a Kähler form, and the B is a class in this commodal space. In this commodal space. Actually, the construction not actually construction, the ideal construction of the local isomorphism is difficult. And first, one find a partial complexification of these model spaces. And then we pick some single points on the complexification of the Kähler model space. The single points are these limits. Then one finds the corresponding complex structure limits in the compactification of the module space of complex structures. And this conjecture mirror map should be determined by the correspondence of these limit points. But actually, the construction is involved. And I will not give the details. From the construction, we can refine, not really refine, we can state another conjecture, which says that for any Calabi-Yau threefold, it admits a mirror such as the Kähler limits, the limits in the compacted compactification of the model space of a complex Kähler form is the same as the limit point of the complex side. And in particular, the complex structure limit is not unique. So a Calabi-Yau threefold may have several mirrors, which means that we can rearrange the correspondence between these limit points. So it can have several mirrors. And for this conjecture, the Calabi-Yau threefold may have no mirrors. It happens, for example, when H2(1) is 0 as before. Now we are going to the final part, which is the homological mirror symmetry. To state this one, we need to recall more, to mention more about the string theory. The strings in string theory are one-dimensional objects, either open or closed. And the endpoint of any open strings satisfies one of some kind of boundary conditions. The Neumann boundary condition or Dirichlet boundary conditions. For the first one, the boundary of the open string moves freely through the space-time and the speed of light. And for the other one, the endpoint is fixed on this boundary. And the D branches are the geometric objects determined by the D boundary conditions, so that the endpoint of open string fixed on that. And homological mirror symmetry is basically an attempt to understand the D branch for the type 2A, for some section of type 2A superstring theory and type 2B superstring theory. Let us recall some mathematical background. And first, we recall that a scheme of which module is coherent if it is finite type, and for an open subset and any integer, non-negative integer n, the kernel of any such morphism is also finite type as an OU module. Then we can the category of all coherent sheaves forms an abelian category, so we can consider the cochain complexes of coherent sheaves. on a projective manifold together with the cochain maps. They make the category of the cochain complexes of coherent shifts. And a cochain map between two complexes is called isomorphism if the cohomology on each degree is isomorphism. And the quotient of this category by this quasi-isomorphism is the divided category of this scheme, roughly speaking. Actually, we will consider a subcategory of the divided category, which contains cochain complexes that are quasi-isomorphic to bounded cochain complexes, which means that the cochain complex is a chain of coherent shifts. It's bounded, means that for some m and n, the stuff outside are 0. Then let us say the symmetric side. A submanifold of a symmetric manifold is called Lagrangian if the restriction of the symmetric form to the submanifold is vanishing, and the dimension is a half of the mother manifold. Together with some extra structures, some Lagrangian submanifold of a symmetric manifold makes a category which is called a Fukaya category. And it is a category we need to describe the home set between two Lagrangians, but it is difficult. It's actually called the Fourier cohomology space of the two Lagrangian. Roughly speaking, it measures the intersection of two Lagrangian submanifolds. For example, if these two sub-Lagrangian manifolds intersect transversally and in distinguished points, then the Fourier cohomology between them is roughly n-dimensional space over some base. So, and similar to the case of the derived category, one can construct a derived category of Fukaya category, which is a little bit more complicated, but the idea is the same. Now let us see the homological mirror symmetry. It's the global picture. In fact, it is a slight simplification of the original mirror symmetry question, because here we only consider the topological sector of the whole superstring theory, and a topological A model is a topological sector of the type 2A superstring theory, and the topological B model is then when the topological the type 2B superstring theory. And for a topological A module, the geometry it based on is the symmetric geometry, and the deep branch, as we have mentioned before, is precisely some special Lagrangians, and the open strings is between the deep branch is the Fourier cohomology space between these Lagrangians, and the category is the Fukaya category. And for the B module, we consider the complex geometry, the complex structure, and the deep branch are complexes of coherent shifts, and the open strings between the deep branch are precisely the home space between two complexes, and the category we consider is the derived category of a variety. But actually, in physics, they consider more than simply the complexes of coherent shift. So that's why I said it is a simplification. In physics, for example, for the complex side, we actually consider some stable complex of coherent shifts. In mathematics, that is called the Bridgeland stable coherent shifts. In physics, it's called the pi stable complexes. I will not mention that as well. Then we are able to set the conjecture. It, as we can expect, it says that a mirror pair admits a certain equivalence between the Fukaya category and the derived category. Here, the derived category of Fukaya category is a suitably modified derived category of the Fukaya category. Actually, this is a very sloppy statement. I did not say anything about which kind of category we are considering. In fact, generally, this derived category is a triangulated category, but this one is an associative infinite category. So to actually give equivalence, we need to lift the derived category in some sense. And this equivalence is not actually equivalence, it's a quasi-equivalence. And in practice, we usually have a family of Kähler threefold for this side. For example, if we have a degree 5, have a surface in P4 for this side, then we will have 3 different constructions of Fukaya categories. I mean, derived category Fukaya categories as well as Fukaya categories. They're called and they corresponding to the whole of a family of Kähler threefold as a mirror, and the special fiber and a general fiber. Okay. That's all of the talk. Thank you for listening.
Okay, is there any question from the audience here or online?
I have one.
What is a keypad?
Okay.
Do you hear me?
Filippo?
Yes, but there was first a question from the audience.
Yeah.
No problem.
What is a keypad?
DPA is, you can think it as an idiopotent combination of the derived category of the Fukaya category, but actually it is not standard notation. I mean, actually the impractical people prove Fukaya the holomorphic mirror symmetry not for category of this form, but as I said before, they have a fine Fukaya category, relative Fukaya category, and absolute Fukaya category, and they manage to modify the derived category in different ways. It's super involved. For example, they prove the derived category for cortex surface. You know, the previous mathematical formulation of mirror symmetry works not only for Calabi-Yau threefold, but for Calabi-Yau anyfold. So for KC surface, from cortex KC surface, the proof for holomorphic mirror symmetry, I think, is about 200 pages. Filippo?
Hi, everybody. This is maybe a tough question. Maybe it's more something to ask to a physicist. But you said, more or less in the beginning, in the middle of the talk, that in string theory there are 6 extra dimensions, and they're supposed to be modeled by Calabi-Yaus. And this follows from works of Candela, Svitene, and others. You said that, which is something that you often hear when you listen to people talking about string theory. The point is, do you have any idea why is it so important there, Calabi-Yaus? I mean, I believe that these 6 dimensions are supposed to be very, very thin, so that we don't perceive in physical reality. And so maybe that is one of the reasons. But why Calabi-Yau? Do they have some special geometrical properties that I'm missing on why they're really suited for these theories?
Actually, I don't quite sure, but the point is that they need the space to be compact complex scalar with a holonomy SU3. They specifically ask for the holonomy.
Mm-hmm.
So that's why this is Calabi-Yau. Actually, I don't understand why the holonomy group has to be SU3.
Okay. Yeah. So it's about the holonomy. Yeah, okay, so probably it's about some symmetry properties that it's hidden
think so.
inside the theory. So how physics thinks about Lie groups as special symmetries of your theories. So it's probably something to be investigated in that direction.
Yeah.
Okay, thank you.
Is there any other question? Okay, actually, I have a question.
Okay.
If you can go, please, to the last slide. Not the very last, but the 20th. Okay. No, the one after this. Yes. Okay. You said that that equivalence between the d pi and the dB has to be thought as some sort of equivalence in higher categories.
Not necessary, but it is proved in this way.
Okay.
Indeed, if you can prove this some kind of equivalence as a additive category, is still interesting.
Okay. But so I mean, what if you consider the underlying standard category of the d pi?
Mm-hmm.
I mean, can you compare it to the standard category, the dB, the standard dB?
I don't think so. For example, the standard one is may not be idempotent complete, but this one always is idempotent complete. So you need to make some modification.
Okay, thank you. Is there any other question? Okay, if not, we thank Ziqi again. And see you next week for the next talk of this seminar. Thank you.